All right, so I want to welcome everyone to Introduction to Ventilation and the latest ASHRAE 62.2 standards. This course is approved for 1 hour in continuing education units, AIA, HSW, AIBD, GBCI, NARI Green, Certified Green Professional, and may be applicable to your local or state-based contractor or design license. My name is Brett Little, and I'm the Executive Director here at the Green Home Institute. Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. And we could not do these sessions without the support of our sponsors, Andersen Windows, Panasonic. Very thankful for their support. Check them out for your fenestrations and ventilation needs. Also, a huge thanks to our members, our raters, our volunteers, presenters, and our board of directors for allowing us to do what we do best. Do you support greener homes? Support our mission. Keep these events free. Make a contribution today or become a member and support our work as well. All right, so I'm going to be handing this over to Jeff here briefly. Jeff, in the late 1990s and early 2000s, managed many different utility programs, supervising a staff of over 30 in making existing homes more energy efficient and comfortable to live in. In addition, for the past 18 years, Jeff has been working with builders to design residential ventilation systems, select the right products, and train installers on proper sizing and installation to ensure better indoor quality and healthier lived-in environments. He is a certified residential ventilation installation Canadian Mortgage Housing Corporation since 2003, I believe. And at one point, he was a HERS Index rater, so he can certainly help speak the language of many of you who are energy raters. So with that, I'll be handing it over to Jeff from Panasonic. And Jeff, feel free to take it away.
Very good. Thank you, Brett. Can everybody hear me? Can you hear me, Brett?
Yeah, we can hear you. Go ahead.
All right, very good. Good morning, everyone, and welcome. Thank you for joining us this morning. Before I get started, I just want to, if you guys don't mind responding, just type in quickly. I'd like to get a sense of the audience here. Do we have some raters joining us? Oops, hang on, my screen went out here. Hang on. My apologies. There we go. Okay, so do we have raters? Do we have builders? Oh, who's got control here? Somebody's flipping through the screen here.
Oh, you're back. You're good to go, Jeff.
Okay, all right. So I want to know if we've got architects, designers, home salespeople, raters, contractors. What is my audience here? If you guys don't mind just typing into the screen here what your, what your background is, what you do for a living.
And just to help expedite this, we've probably got 50% of the folks in the room are architects, maybe
okay.
20% are consultants, and then we've got a mix-up of contractors, government, manufacturers, nonprofit, and maybe about 5 or 6 energy raters.
Very good.
So welcome, a diverse crowd here.
Yeah, excellent. All right, so again, the course today is Introduction to Ventilation. Our objectives for today are to understand the necessity for ventilation, understand the ASHRAE 62.2 code, both the 2010 and 2013 version, and then understanding whole house, intermittent, and spot ventilation, and then evaluate exhaust supply and balanced ventilation, and then to calculate the proper size for a ventilation system, and then understanding some of the fundamentals of installation, because as we know, we can buy the best ventilation equipment in the world, but if it's installed improperly, it's not going to work properly. So, and then if you have other questions later in the presentation here, you'll see my email. You can ask the questions here today or follow up after. So let's get going. I want to also tell you that this is the first time I've ever done a webinar, so I'm used to doing this presentation, but I'm used to walking around in front of an audience doing it where I have eye contact and whatnot. So this will be a little bit different for me this time around too. So hopefully I can do a good job at the webinar as well. So the first thing we want to talk about is why we need to ventilate. I didn't put these slides together, but I do like this first slide because I grew up in a little town in central Wisconsin, Rudolph, like Rudolph the Red-Nosed Reindeer. And we did, in fact, go out at night and catch fireflies in a jar and put them on a shelf and, you know, watch them blink while we talked as young kids and fell asleep. But when we woke up in the morning, oftentimes the fireflies didn't because we didn't know enough to put, you know, holes in top of the jar lid so that they would get some fresh air. Well, over the past 20, 30 years, home builders have gotten much better at making our homes tighter and tighter. And that's good because people will not accept an uncomfortable, drafty home anymore. But in doing that, they've made it, you know, similar to that jar with the lightning bugs in it, or the lightning bugs in it, and you know, the air trapped inside creates an environment for the occupants that isn't as healthy. So with those tighter homes, that envelope is tighter. We can't rely on the natural leakage of the building anymore to supply fresh air and a healthy indoor air environment for the occupants. So now we have to, you know, ventilate mechanically. And you know, a lot of things have changed about the way we build homes now compared to 30, you know, years ago. And you see a list here of some of them. And some of the most important, you know, in my opinion, are like the insulation. You know, years ago, how much spray foam insulation did we use, for example? There was very little spray foam used, and when it was used, it wasn't used to seal the mud sill, for example, or to seal the penetrations for plumbing or electrical. So the application of the spray foam has made a significant improvement in the comfort of homes, but in tightening up that building shell, we've also now trapped a lot of the pollutants that come out of the building materials, but also, you know, that we bring into the home. And as far as the mechanical systems, you know, a lot has changed there as well. And this is a question that I'd like you guys to answer if you can. You know, where did the combustion air for the furnace come from 30 years ago? Exactly. It came from inside the home. It was sucked in, you know, through the mechanical room, into the furnace, through the combustion chamber, and out the chimney. Well, that was ventilation. That was forced ventilation in the home. And today, we suck that air through a plastic tube into the furnace. It goes through the combustion chamber and gets blown back out. So even that ventilation, in addition to sealing up the home and making it more airtight, we've eliminated some of the ventilation that the furnaces used to provide. So, you know, we have to do something to make up for that. In multifamily situations, the problem can be even worse for a couple different reasons. In a single family home, the exterior surfaces are to the outside, and if those surfaces are leaking, which they all leak some, you know, there's an opportunity to bring fresh air in or leak stale air out of those surfaces. But in a multifamily situation, the exterior walls of one unit are either the exterior walls of a common area, or they can be the exterior walls of another unit. So the air being exchanged through those surfaces is oftentimes air from an adjacent unit up above, down below, And in some cases, the exterior surface could be a garage. And we have that in single-family homes with attached garages as well. But in multifamily situations, because we have such a reduced amount of surface area exposed to the outside, and the building materials in multifamily are often a little bit lower grade, so they might off-gas more. So we've got a situation in multifamily where we have an even larger need probably for mechanical ventilation. All right. So before we move on, does everybody agree that we need to mechanically ventilate in order to have good indoor air quality? That was our first objective here today. Very good. I've got one yes. Thank you. I appreciate the participation. Again, I'm used to doing this in front of an audience. So.
And if they're not, perhaps they're in the wrong place. So if they don't agree.
There you go.
You might want to just go now.
All right. All right. So now, knowing that we need to ventilate mechanically, let's move on to talking and learning a little bit about meeting ASHRAE 6222. And I should also say that, when you're talking about building codes, oftentimes the codes themselves will not refer to ASHRAE 6222. They'll refer to the mechanical code or the residential code, but they're referring to, or they'll use the calculations exactly as they are in ASHRAE 6222, whether the 2010 or the 2013 version, but it won't refer to ASHRAE oftentimes in the code itself. But the numbers will end up being the same. Across the country, you'll have many different programs: Building America program, the Lead for Homes, Energy Star, American Lung Association, Healthy House. Each of those programs will defer to ASHRAE 6222 for their ventilation code. They don't create their own ventilation code. They refer to ASHRAE 6222 or the calculations or the chart within ASHRAE 6222, rather than trying to design their own standards. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers, as you can see here, and they, will update this standard just like all of the other building codes every 3 years, and there will be addendum added throughout the year, sometimes or between updates to improve the code or the understanding and clarity of the code as well. So, and most of you are probably familiar with this, whether it's ASHRAE or other building codes. All right, the Home Ventilating Institute, HVI, is the third-party testing organization for ventilation equipment. Anybody who manufactures fans, ERVs, furnaces, all of that equipment is tested by the Home Ventilating Institute. They're the UL, if you will. You wouldn't buy a VCR or a DVD player unless it was tested and approved by UL, and the same is true of ventilation equipment. You wouldn't go to market with a product that wasn't tested by HVI, because basically it wouldn't sell. Also, HVI is the organization that certifies a piece of ventilation equipment as Energy Star rated. So if it meets a certain efficacy with CFM per watt, it will be HVI that's doing that testing to give it its Energy Star certification. And they also test for SON levels or noise. All right, some basic terms here for ventilation. I'm sure you all know what a CFM is, cubic feet per minute. That's the volume of air. And SON is a measure of the noise. And what we often use as a kind of a reference point is if you walk out in your kitchen in the middle of the night and your Energy Star refrigerator is running, that real quiet hum, that's about 1 zone, just to give you some kind of reference. Probably the one that people may not be quite as familiar with is static pressure, and that's a measure of the resistance to airflow that a fan might meet with ductwork and the termination. So the higher the static pressure, generally speaking, the more resistance there is, and the lower the CFM would be for that product. It has a negative impact. The higher the static pressure, the more it will impact the performance of the equipment. And that's why we're going to talk near the end of the presentation about proper installation, because as I said earlier, you can buy the best equipment in the world, but if it's installed improperly, or you add too much ductwork or a poor termination, the equipment's not going to perform the way it's designed. So that's the important one there. And as the chart here shows, as you increase the static pressure, the airflow will generally be decreased. So HVI will test the equipment for bathroom fans at 0.1 inches of water gauge. But that's often not a realistic install. You know, how many of our audience does actual install work? Is there anybody that I can ask a question of that's doing actual installs of bath fans or HRVs, ERVs? For an answer here, but generally speaking, what I would do is ask the audience, and the question would go, you know, is 0.1 inches of water gauge a realistic install? And the answer is usually no, because that would be about, you know, 8 feet of straight pipe, 1 elbow, and then out through the termination. And it's very unrealistic that in today's homes with bathrooms located in the middle of the floor plan, that you can get out to the exterior of the building with just 0.1 inches of water gauge in terms of ductwork. So we feel that 0.25 is a better number to test at. So oftentimes, you know, you want to, the fans should be tested, we feel, at a higher water gauge. 0.25 or, is more realistic for a residential install. So we test all of our products at that and publish that information on all of our products. I don't want to get too much into product, but just wanted to mention, you know, that 0.25 is a better representation of what fans actually are installed with in terms of static pressure. And if you've walked through any new construction, you've probably seen some of what's on the screen now. Ductwork draped across trusses. I often refer to what I call the potato chip install, where it dips between each truss, and that has a significant impact on how much resistance there is to the ductwork. Flex duct, you know, has about twice the amount of resistance as hard pipe, so, you know, we want to always try and reduce the amount of static pressure by reducing the number of elbows, you know, keeping the runs nice and short, and making sure that they're terminated to the outside, but with a termination that doesn't cause too much resistance. And then it's not uncommon also to, during the install, you know, you need to fasten the ductwork to the unit. Has anybody ever seen an install like the middle picture here, where the damper is pinned shut by the screws that are installed to hold the ductwork on? I was at a job site in Seattle 6 months or 8 months ago, and The ductwork was connected with 3 mechanical fasteners by code, and all 3 of those mechanical fasteners, all 3 of those screws were installed in the bottom, and all 3 of them were installed so that they would conveniently hold the damper on the fan shut. So you can imagine the performance issues that, and that we were called to the job site due to performance issues. And we found that not only was the wiring wrong and the exterior termination was painted shut, there were 3 screws in all 150 fans holding the damper shut. So a very interesting call to go out on. We were called out, of course, because the equipment was failing. But when we got out there and did the investigation, we found that there was just too much static pressure because the damper was pinned shut and the exterior termination was painted shut. So once we fixed all of that, everything was fine. All right, before I go on, any questions about static pressure, zones, CFM? All right, Brett, just pipe in here anytime if you see a question that we want to address. Okay.
Sure.
All right. All right. So the people who do, I know that we have a bunch of raters here, so you folks know most of this information already. But when you're enrolled, or your buildings are, your homes are enrolled in any of the programs that we talked about, or built in states where the code requires it, it is important that all of the bathroom fans be measured. It used to be okay years ago to buy a 50 CFM bath fan, that was rated at 50 CFM, install it, and you were good to go. Well, that's no longer the case with ASHRAE 62.2, or most ventilation codes. It would be required not just that you buy a 50 CFM fan and have it measured, not that you just buy a 50 CFM fan, but it actually be measured and be able to perform at a 50 CFM level. Excuse me. Or it has to be tested and perform at the level required by the ASHRAE 62.2 for the whole house ventilation requirement, which we're going to talk about how to calculate that or find that using the chart. But it's no longer acceptable just to install equipment rated for a certain CFM. It's important that now it be tested, and our HERS raters are the people who will most likely be the people doing that. You see the picture of the gentleman in the top right-hand corner. They're holding a bolometer. That's a device that measures airflow in two directions and gives a readout so that the rater can put that into his report and verify that the fan is testing at the minimums to meet the code. And we want to keep those measurements or that airflow calculation performance between 100 and 120%. 100%, of course, because that's the minimum and you have to meet code. But we don't want to go, too far over. We don't want to take the Tim Taylor approach and go, well, if 100 is good, 150 or 200 is even better. We want to keep it within, 20% above, because we don't want to be wasting energy to overventilate the home, and we could create conditions within the home that we're uncomfortable by overdrying as well. So. And for meeting the continuous supply exhaust ventilation code, we need to keep the zone rating at 1 zone or less. And why would we want to do that? Does somebody know the answer to that? What we have found in the past is if the ventilation equipment is too loud, the occupants will disable it, whether it's a homeowner or a multifamily occupant. They're going to disable that ventilation equipment and stop it from doing its job because they don't want to listen to the equipment run. And with the ASHRAE 62.2 code, it also has to function automatically. We can't rely on a multifamily occupant or even a single home occupant, homeowner, to run the equipment. It has to be automatic. So we would have it programmed to run either intermittently X number of minutes per hour or continuously to meet the number of CFM that we need exchanged from that building on an hourly basis. And the equipment must be ENERGY STAR rated. All right.
And if I could, interject real quick, we verify a lot of homes, and even in states without codes where you need to test this equipment, if folks are using LEED or Green Star or National Green Communities, there's extra credit for the testing, but it's not required. But we would say that if you're hiring a contractor or a rater, that's something they should just be doing. Get that extra credit, because a lot of times we see, unfortunately, when in real projects, when they go to test the system, typically there is something wrong, and it just needs a slight adjustment. So, I just want to second that and highly encourage that.
Very good. All right, so ASHRAE 62.2, we used to actually have to buy a manual years ago, but of course all this information is available online now. That give you a little date myself there a little bit, but we used to actually have to buy a manual every time it was updated. The code, ASHRAE 62.2 code, refers to single and multifamily properties up to 3 stories, but it does not address thermal comfort. This is strictly air exchanges, and this does not, we're not talking about our manual D or a manual J here and getting the right number of BTUs in each room. This is just referring to the ventilation component. And of course, the goal is, we want to create a healthy indoor environment for the occupants. But in addition to that, we want to manage, ASHRAE wouldn't refer to moisture as a pollutant, but we also want to protect the building and make sure that we're not having deterioration due to moisture issues. There's a lot on this slide, and I'm not going to read it word for word, but there are a couple things that I want to point out. So on the ASHRAE 62.2 code, there's going to be a 1% calculation on the square footage for the building. And when we talk about the 2013 version, you're going to see that that number goes up to 3%. And we'll talk about why that is. And there's a couple of different ways, of course, that we can meet the code. We can meet it by running a fan at a low speed continuously. And that's often the preferred method because it's constantly refreshing the air in the home. Or we can run it at a higher CFM on an intermittent basis. So if the home required 50 CFM of continuous ventilation, we could buy a fan and install it and run it at 50 CFM, or we could have a 100 CFM fan running for 30 minutes an hour. And as long as we accomplish the goal at the end of the hour of removing the amount of air required based on the number of bedrooms and the square footage of the home, that's we've met the code. So there's 2 approaches that we can do to meet that, and the equipment that you install will determine how you want to do that. All right, and then, well, we're going to talk about spot ventilation a little later, so I won't go into that now. And let me see, I've got a question here, or I'm not sure what the question is here. 1% of gross floor area or net conditioned space. I believe it's conditioned space, if I'm not mistaken. If anybody knows the correct response there. Brett, do you know the answer to that? There we go, conditioned space it is. Thank you, Kevin. All right, so here we are, the ASHRAE 62 2013 version. Again, we're looking at a 3% calculation here. I don't know many states that have adopted the 2013 version. I think California has looked at it. I'm not sure that California has even actually adopted or has implemented it yet. Most states are using the 2010 version with the 1% calculation. One thing I should point out, though, and you see it's highlighted there near the bottom of the slide, is that the owner has control over the ventilation system. And of course, in a single-family home, that's going to be the owner, if it's an owner-occupied single-family home. But in a multifamily situation, because the building owner, is the person with the investment there, and occupants will often disable ventilation and create a situation that might be damaging to the building by not removing moisture, and also, deteriorate their own indoor air quality living space. It's important that the owner have control over that system so that they can protect their investment and, hopefully create indoor air quality situation that's better for the occupants on the multifamily. All right, before we go on to the 3 different types of ventilation, I just want to pause and give Brett an opportunity to speak, or if anybody's got a question, before we move on to the 3 different approaches to ventilation.
Yeah, Jeff, I had a quick question that I've seen kind of go in the opposite direction of these zone ratings, where you had mentioned that the improper zone rating, it could be too loud, so the homeowner or resident might shut it down. But I've heard the quite opposite, where it might be too quiet, and someone who's used to that sort of loud ventilation, sort of, they go in the bathroom, they hear that, they're like, okay, great, no one can hear me now. I feel comfortable. What are your thoughts to sort of folks who might think, hey, you should upgrade, it's going to be super quiet, and then they might go, geez, I liked it when it was loud?
Yeah, that's a tough one, and that is often the case with that, powder room off of the kitchen, right? You have guests over, and the guests go in, and of course they don't, want to be heard doing their business, shall we say. So that could be a tough one. Years ago people would say, oh, turn the faucet on, and that'll cover the noise or whatever, but we don't want to waste water either. So yeah, that's a tough one. And again, we don't want equipment that's so noisy that it'll be disabled. So and the other side of it is, we'll get complaints that the equipment's not operating, not because it's not operating, but because they can't hear it. So, there's a couple of things that come up from time to time, that you might get callbacks on, but that's a tough one. It's not noisy enough. Well, you got to make some noise somewhere else and turn the radio on, or turn the water on, or something like that to cover those noises if you don't want people to hear you.
I think of the same issue they have with electric cars, where no one could hear them coming, so they had to put a device in it to make a noise. Has Panasonic or anybody thought about that?
It would be counterintuitive to our goal. We want to make ventilation equipment, of course, that performs at the highest possible standard and delivers the air that we want to deliver. But in most situations, it's actually static pressure that creates the noise by making the fan work harder. So we don't necessarily want to create a condition where the ventilation equipment would be noisier.
And there's somebody here chiming in, requirements for one zone is only for continuous. Choose an intermittent if you want noise. I don't know if that can help solve the problem.
Yeah, so the spot ventilation requirement, I believe, is a 3-zone limit. And let's see, who made that comment? David. Oh, I'm sorry. My text here is so small. It looks like Christina made that comment. Yeah, and I believe that on the spot ventilation side of things, it's a 3-zone maximum. So,
okay. Great.
All right.
Thanks. Yeah, let's head on.
Yeah, let's move on to exhaust supply and balance ventilation. So there's 3 basic approaches to meeting our ventilation requirements. We can do exhaust ventilation, which is essentially, what we've been doing in homes for years, using exhaust fans in the bathroom or in the laundry room. The kitchen range hood would be considered an exhaust fan as well. We can use continuous supply. This is generally met, or this approach is often with a damper and a duct running from often the sill box into the cold air return of the furnace. There's usually a control of some type on the furnace that tells it to run X number of minutes per hour. Air cycler makes a switch, and then also Honeywell and April Air have switches like this that are based on the air cycler technology from years ago. So these will be tied to that damper. They'll both turn the air handling unit on and open the damper and supply air through the negative pressure in the cold air return for in a forced warm air furnace situation. And then finally, we have a balanced approach, which is ERVs and HRVs. That will be taking air in the building or out of the building, or I'm sorry, taking air into the building and out of the building in equal portions at the same time, thus a balanced system. And again, not to get too heavy into product, but Panasonic has a similar system without heat recovery called the select cycler system. So those are the 3 approaches that we can use to meet our requirements. So and we're going to go into each of them in a little bit more depth here. The one thing that I do want to mention is that with each of the, as we go down the slide here from exhaust to supply to balance, we're also increasing our cost as we go to each approach here. So exhaust-only ventilation is the most cost-effective. Supply is the next most cost-effective, and balanced is the most expensive. And I'll go into that in a little bit more detail as we go through here. So as I mentioned before, exhaust ventilation is simply using an exhaust fan, often placed in the bathroom, to meet our ventilation requirements. We've been using bath fans for many years. To use them as a whole house ventilation system really means just upgrading to a better bath fan that runs quieter, is rated to run continuously, and to do its job, hopefully unnoticed, in relying on the building shell for the makeup air, if you will, or the fresh air. Again, this is the most cost-effective means to meeting your requirement, because you're just buying a little bit better bath fan and using that, doing your calculations, and then programming that fan again to run automatically without homeowner or occupant interaction to meet the code. There's pluses and minuses to each of these systems as well. And for example, one of the potential negatives for combustion appliances, or for the exhaust-only approach, is that if there's a lot of ventilation required, you could create some negative pressure within the building. And if you had a B-vent water heater, for example, or a naturally aspirated water heater that's relying on the heat in the combustion gases to heat the water, to exhaust that air or that those combustion gases, and it's maybe not set up perfectly and doesn't obtain a draft real easily, you could potentially create a backdraft situation in a home and suck those gases back into the home. And then people might argue against that. Well, a dryer, for example, has much more CFM than your continuous running ventilation equipment might have. So if the equipment in an exhaust-only situation is going to do that, certainly a dryer would do the same, or a kitchen range hood. Another criticism of the exhaust-only ventilation approach would be that the air is not filtered. You can't filter it like you would in a supply ventilation system, where you're pulling it in through a duct and running it through or across the furnace filter before it's delivered to the home. And that's true. And you don't know, where that air is coming in through the building shell. Chances are it's coming in through the closest, the openings in the building shell closest to where the fan is. And if that's a crawl space or an attic hatch, or someplace where there might be undesirable air, you certainly could be dragging things in from those spaces that you don't want in your home as well. So those are some of the negatives to the exhaust-only approach. But you'll see in the top right-hand corner, though, that for northern climates, this is often the best approach, because if you're relying on dragging in cold air during the winter months to meet the requirement, that air can have a drying effect on the building shell. And when we talk about the supply-only ventilation, we'll explain why that might not be the best for a northern climate. Another thing that's, one of the pluses for exhaust-only ventilation is it requires very little homeowner education. You set it up, do your calculation, program it to run automatically, and there's no filters to change, there's no interaction from the homeowner, and very little education that has to be done. And as I mentioned before, it's also usually the least expensive system to use. So let me just take a look at this. Again, I think it's Christina here is saying exhaust only risky if radon is a hazard. I'll address that as best I can. Paul Francisco from University of Illinois has done a recent study. I don't know that it's been published yet. And the results of that study were, in fact, that negative pressure in the building or exhaust-only ventilation systems do, in fact, not increase the amount of radon in the home. That's the most recent information I have. And if anybody else has information to the contrary, I'd be interested to learn about that. If you could send me a link, that would be very good. All right, so let's move on to supply ventilation. Here, as I mentioned, we're relying on a duct running to a fan in the building, which is forcing air into the building and relying on the building shell to relieve that pressure. It's a little bit more expensive here because we're not just upgrading a bath fan. Now we're installing a control unit on the side of the furnace. We're installing a duct generally that runs from the exterior of the building to the cold air return. And we're operating a damper with that control as well that is normally closed until the controller says that it should open and turn the air handler on. So those are additional costs, to having this system. Now, the advantages, of course, are that when that air is brought into the cold air return, it's going to be run across the furnace filter before it's delivered to the occupants. So that's a plus. And because it's not creating negative pressure in the building, we're not going to have the potential to impact in a negative way the combustion appliances like the water heater, for example, or a fireplace might also be susceptible to spillage if we had too much negative pressure in the building. And then, we also want to, well, here's a diagram, and it shows, and this is a little bit easier for me to explain, if this is an in-person presentation, but in the diagram you see here, running from the right-hand side of the house over, let's say, the picture window, is the ductwork coming into the building from the outside. Some of the depending on the climate that you live in, I guess is the way I'll say this, is that this supply-only approach is generally considered better for hot, humid climates than it is for cold climates. In a cold climate, if you're forcing air into the building and relying on that building shell to allow air to leak out, when it's minus 10 degrees outside, if you're taking indoor air that's at 62 degrees and 40% relative humidity and pushing it through the building shell, I think we all know what's going to happen when that warm, relatively moist air hits those exterior surfaces at minus 10 degrees. Certainly if it leaks through a electrical outlet or something like that into the wall cavity and then hits those cold surfaces, we're going to have some condensation in those wall cavities, and then you're going to get conditions like this. Now, that could have been a flashing issue as well, but you're going to get moisture in those walls, and eventually that moisture will potentially lead to mold. So we want to make sure that we're using the right ventilation system for the climate. In a balanced situation, and many professionals in the field will argue that this is the best ventilation for every climate, and I won't disagree with that. But it is significantly more expensive, and we're building homes for homeowners who are making cost decisions all the time, and this is the most expensive system because now we're not just upgrading a bath fan or adding a simple piece of ductwork with a control and a damper. Now we're adding a piece of equipment that needs to either be ducted independently, or it needs to be ducted to tie in with the furnace system and be synchronized so that it's going to be running at the same time the air handling unit is to distribute the fresh air throughout the building. So not only are we increasing our upfront cost by adding significantly more expensive equipment, the equipment itself uses some energy to run, and then if it's interlocked with the furnace motor, that's going to also add additional operating costs. But there's also a great deal more homeowner interaction, education that has to take place here, because someone's going to have to open this equipment up 3 to 4 times a year to clean the filters out, and once or twice a year pull the core out and vacuum that core off. So there's a significant upfront cost. There's a significant, there's an additional operational cost, and then there's a maintenance cost as well. So while I will agree that this is the best ventilation approach for all climates, there are also some detriments to this in terms of expectations from the homeowner to maintain the equipment. And I think we struggle to get homeowners to change their furnace filter, getting them to open an HRV or an ERV and do that 4 times a year to keep it clean, and then also be conscious enough to go outside on the exterior of the building and clean the intake out, because if Junior is out there mowing the lawn and he points the chute towards the home, and the intake for the HRV or ERV supply is low to the ground, those grass clippings are going to blow up against the side of the house and can plug that intake. So we have to be very conscious of keeping all of the equipment operational. And I think when homeowners are making their choices in terms of what they want to invest in their home, you know, this type of equipment, I think, often goes by the wayside for eye candy, let's say. So, but again, I will agree that, you know, if you're building in Fargo or Miami, you know, the equipment that's balanced might do a better job over a wider climate range than either the exhaust or supply approach. All right, let's just keep moving here. Well, and here's where I was going with that comment is, you know, the ventilation system that you choose, whether it be supply, exhaust, or balanced, you know, you have to consider where that building is being built. Whether it's in Fargo, North Dakota, or Miami, might have a significant impact on where you're going or which ventilation system you choose for that home. All right, so I'm going to pause here, and I'm going to look at a couple of these questions here. And David is saying...
and real quick, while you're answering those questions, and because we're coming up on our time at 1 o'clock, though we're going to be going on a little bit more, for those of you looking for your GVCI continuing education, a little bit different than we normally do it. I just sent it through the chat. So make sure to capture that number and report it there, as it will not be coming through the email.
Very good. Are we going to get cut off at the time limit, or are we going to be able to?
No, we're gonna have time to keep going here.
Okay.
But some folks may have to leave around 1:10 or so.
Okay. Very good. All right. So I will keep moving here in terms of. Spot ventilation, again, you know, we've been doing this for years in homes, whether it's over our range hoods to remove cooking odors or in bathrooms to remove moisture and odors. You know, the spot ventilation is just the exhaust appliances that we've been using for a long time. So, you know, the requirements, you know, here for bathroom fans is that they can do, they're capable of doing 20 CFM continuously or 50 CFM intermittently, and you know, there's some zone ratings that go along with that as well. As was pointed out earlier, the intermittent requirements are below 3 zones or less, and for continuous ventilation equipment, we want to keep it 1 zone or less. Those are, of course, rated, and actual installs can have an impact on how noisy a piece of equipment is. In terms of sizing a bathroom fan, you know, there's a couple of different approaches. You can use 1 CFM per square foot. You can do a volume calculation, whether it be V5 over 60, you know, which is what's put in here. So there's a couple of different approaches that you can use to size a bathroom fan, for example, to exhaust the moisture. Let's see here. Cooktops must be able to do 100 CFM in order to meet the code. I don't know. I haven't seen a HERS rater test a range hood, to be honest with you. So I'm not sure how often that's actually being done, but I do know that, for example, in some of the codes, you can use an unvented range hood as long as there's another fan in the kitchen that's capable of running at 100 CFM to meet the requirement for the kitchen as well. So another approach there, if you don't want to actually vent the range hood. I recommend that you do vent the range hood because there's a lot of pollutants that come off of that range hood that aren't good for the home or the occupants. I'm going to skip over garage ventilation because we are running low on time, and I don't know a single state that has a garage ventilation requirement at this point. It's probably coming in our future, but I don't know of anyone who is actually using that approach or requires that at this point. As far as calculating, and all of this information is available online, but just real quick, if you take a look at the left, you can see that the calculation there is that we want to have 7.5 CFM, it's per bedroom plus 1, because we're going to assume there's 2 occupants in the master, so you count the bedrooms, add 1, and then multiply times 7.5, and then on the 2010 version, we're using a 1% floor space or conditioned space calculation. And for this home here, the 2,600 square feet, 4-bedroom home, you're going to see that we would require 63.5 CFM. And in the 2013 version, using that 3% conditioned space floor calculation, conditioned space calculation, that number would go up to 115.5 CFM. There's also charts available, and Michigan, for example, doesn't make homeowners do a calculation. They just have a chart that is referred to in the code, and you just you look at the number of bedrooms and the square footage and come up with the number that's required, and that's all that's required in Michigan, and I'm sure there's other states that just use the chart as well. Here's the 2013 version, and you can see, for the same size home, that there's a significant difference. Going back to the 2010 chart here. It was pretty small. There we go. If you take a 4 to 5 bedroom, 1,500 to 3,000 square foot home, 2010 version, we need 75 CFM. And if we look at that same home in the 2013 version, 15 to 2,000 square feet, let's say, we would need, in a 4-bedroom at 3,000 square feet, we would need 130 CFM. So it's just an easier way to get there. The number of CFM, I won't say is not the important thing. The important thing is that we're getting some ventilation in the home. And again, I don't know anyone who's using the 2013 version at this point. So mostly we'd be looking at the 2010 version. Here's a chart right out of the. Go ahead.
I was just going to say, for those, a couple people had questions, I think, about getting the slides, primarily, I think, to get access to these documents. But I assume these documents are available, whether it be the code or whether it be ASHRAE. These charts are probably available on the website or on the code
they
website.
Are. Yeah. In fact, if you happen to take a look at, and again, not to get too salesy here, but the codes or these charts are in the Panasonic catalog in the back, and they're also available online. So you can certainly get that information online just by going to Panasonic/ventfans.com. This chart here is actually right out of the Michigan updated codes that went into effect on February 8th, and it's just a copy of the ASHRAE 62-2010 chart if you look at all of the numbers. All right, last section here is on installation, and we can go through this pretty quick. I've helped a lot of different organizations, a lot of different companies over the years with installing equipment properly. I've swam through more fiberglass insulation than I care to tell you about, and itched and itched and itched for days afterwards, both on my skin and my eyes and respiratory parts. So the simplest way that when I talk with contractors about installing their equipment so that it will perform at its best, is I tell them, kiss your ductwork. And that might seem a little odd, but if you keep it short, keep it straight, and keep it smooth, those simple things are going to significantly improve the performance of the equipment. And then the other component, of course, is to make sure that the termination that you're putting on the end of the ductwork has enough net free space that it can easily allow the air out. Years ago, people would use those silver vents that were in the soffits as a termination, and those things have a real tight screen on them and would plug up real fast. So not only do we need to keep our ductwork short and keep it straight by reducing the number of elbows, and preferably if we can use a smooth ductwork like a galvanized pipe or PVC, but we also want to make sure that the termination that we're connecting to the end of the ductwork doesn't offer a lot of resistance. Where we're putting that termination is important too. A lot of people don't like to poke holes in the roof and create opportunities for leaks, so we see a lot more terminations in the soffit. And the soffit is usually the quickest way out of the building, which helps us keep the ductwork short and straight. But we have to be aware of where we're putting it. And if you take a look at this install, you'll see that there's a vented soffit panel adjacent to the exhaust termination, which could create an opportunity for warm, moist air to be sucked right back up into the attic and cause potential moisture issues up there. So we want to make sure that if we're terminating in the soffit, that we're putting it in a solid soffit panel, and that there's two solid soffit panels adjacent to the one we're installing it in, so that moist air has an opportunity to escape from underneath the soffit and not be drawn up into the attic. And also a termination that points the exhaust out from underneath that soffit, rather than this unit here I'm familiar with, because it will actually allow the air to escape in 3 different directions. So you want to make sure that it's being terminated in such a way, if you're using a soffit termination, that it's not going to create problems in the attic. And if you're familiar with ESPN, you'll be familiar with this come on, and when I'm in an audience situation, I will talk about this a little bit more. But you know, really, if you see this type of install when you're inspecting homes, you know right away. You know, we've got flex duct being used here, which is fine. You know, that's the most common install. But you know, let's at least point the fan in the direction of the termination. You know, the one on the right here, where we come off of the fan and we immediately do, you know, 1, 2, 3, 4 90-degree turns with flex duct before we're, you know, a foot away from the fan. You know, is absolutely a terrible install. So we want to be, you know, looking for these types of things and helping our ventilation equipment do their job, do its job that we designed it for. Okay, so that's the end of our presentation, and now hopefully everyone understands the necessity for ventilation, has a understanding of ASHRAE 62.2 and how to calculate both the 2010 and 2013 versions. We have an understanding of whole house intermittent and spot ventilation, and we have an understanding of exhaust, supply, and balanced approaches to meeting the ASHRAE 62.2 code. And you know, we know a little bit about installing it properly, so with that it'll perform at its best and to meet the design codes or the design requirements that we want it to. Brett, back to you.
Yeah, guys, we still have some time here for Q&A for those of you listening here live. Survey should be coming your way, so make sure you take that, whether you need continuing ed or not. We dropped in the GVCI number into the chat, so if you didn't see that, let me know. I'll get it back in there. For those of you listening on demand, so I'm not talking to any of you right now, those of you listening to the recording, make sure to take your 10-question quiz at the end to get your CEUs, and you'll be good to go there. So feel free to drop in some other questions here. Jeff, I have a question here for you, and I'm as we're waiting for the audience to throw in some more, and I'm throwing up an image here to help reference my my question. Let me see if that image is coming up here. So These folks, these renegades, as you may call them, or as you may know, over at the Building Science Corporation have come up with their own standard to oppose ASHRAE because they, from my understanding, feel that the ASHRAE requirements may actually over-ventilate a house. So do you have any initial thoughts or any experience with utilizing their standards, or have you heard of this, or any comments there?
I have not used their standards in any manner.
Okay.
Not that I think it's bad. I just, it's not part of my work scope. And the people who are having this debate, whether 1% or 3% or some other number is the right number, honestly are a lot smarter than me. So, far be it for me to question people who know a whole lot more about this than I do. And at one point earlier I mentioned, whether you're using the 2010 or 2013 version, and I said, how much ventilation, as long as we're getting some ventilation and some air exchange. I kind of, was kind of referring to this debate when I made that statement. It's, every household is different. The number of occupants, the number, one of the things that we don't look at when we're, calculating the amount of ventilation a home needs is we don't look at the number of pets, for example. If I've got 3 dogs and a cat, I think pets require, in terms of maintaining air quality, probably require as much or more than humans do because they're there all day. So, there's many things that impact the indoor air quality, and I don't know that we take all of the things that have an impact into consideration when we're doing the calculations. So I'm sure that doesn't answer your question, but those are certainly some of the things that, have an impact on the indoor air quality. And like I said before, the people who are having this debate, and this debate's been going on for, 4 or 5 years now, they're a lot smarter than me, and I'll defer to them to come up with the right answers.
I'm trying to see. I see several comments and people letting us know who they are, so that's great. Thanks for that. Feel free, if you have a specific question, to put that in there. So does the whole house exhaust fan in the bathroom, does that also accommodate the bathroom exhaust requirements?
So the answer is generally yes. What you would do is have a fan that would run very quietly in the background at a continuous rate to meet the number of CFM required by the code, whether it actually refer to ASHRAE or some other code. But essentially that calculation, based on the number of bedrooms and the square footage of the building or the conditioned space, excuse me, and it would run at that lower speed on a continuous basis, and then there would be some mechanism, whether it be a motion sensor or a switch, that would kick it to high speed when someone is going into the bathroom to create odors or moisture, essentially.
Mm-hmm.
And that minimum requirement can be split amongst a number of different bathrooms or something like that. If you want to, if you don't want to have a single bath fan running at 100 CFM, if that's the calculation for that building, that it needs 100 CFM of continuous ventilation to meet the code, well, maybe you want to run 2 bath fans, one on each floor at 50 CFM continuously to meet the code, and those would, both have boost functions on them so that when the occupants were creating moisture or odors, that it would run at a higher CFM to exhaust out the pollutants, if you will.
Okay, great. Well, we're at our time here, so we're going to go ahead and wrap the session up. If folks have some more questions, especially on Panasonic, feel free to stick around, Jeff, if you've got a little more time, but we're going to wrap the session up here. Jeff, really thanks thankful for your time, thankful for Panasonic for all your education and awareness that you do on these topics and helping us make our buildings better. Jeff, where can people find more information about what you do and about ways to find better products for ventilation systems?
Certainly you can go to Panasonic/ventfans.com, and a lot of the information that I shared with you today, for example, on how to size a bathroom fan or how to calculate the static pressure, you know, that each elbow and each piece of ductwork might add to an install will be available there, and it's also available in our Panasonic ventilation catalog.
Great. Thank you, Jeff. Thanks, everyone. Take care.
Thanks, everyone.